All right, guys. Here we go. Um, so we're going to start 7.3, which is called Multivariate Linear Systems and Row Operations. No, I did not. Okay, so allow me to translate for you. Multivariate linear systems. Multi means many, multiple, more than one. Variate sounds like the word variable. Multivariate, many variables, multiple variables. Linear makes a line. Systems, lots of equations together. So there are linear systems, so there's lots of linear equations using lots of variables. Okay, we've kind of looked at that. So equations that have like maybe x, y, and z, several of them, that sort of thing.
For those last two problems on the homework?
Yes, yes. And then row operations. This is a new technique that we're going to use to solve systems by hand. And like I said, this is kind of the basis for linear algebra. They take these ideas and then it kind of expands off of there. But solving systems of equations is kind of like the immediate goal that kind of gets everything started here. Okay, so there are some rules that we need to abide by when we're doing this. And those rules all come from rules that you already know about when you're solving a system by hand. So let's say I had something like 2x plus y minus z equals 3, and x plus 2y plus z equals 1, and negative x minus 3y minus z equals negative 2 or something. Okay, so I'm not even sure if this system has a solution or not. I'm just using it as a means to kind of explain some of these rules. So there's a corresponding matrix equation that we can make from this that we've talked about, right? Okay. We're going to do that same type of thing here to do these row operations, but we're going to take it and turn it into what's called an augmented matrix instead. Okay, an augmented matrix essentially is a coefficient matrix augmented with, which means it has something added to it or is an extra little piece that goes with it, augmented with the answer matrix. Okay, so we've got the coefficient part here, 2, 1, negative 1, 1, 2, 1, negative 1, negative 3, negative 1. And then the augmented part is just a straight line. It's not the edge of the matrix. It's just a straight line up and down. And then on the other side of it, 3, 1, negative 2. Okay, so it's the coefficient matrix and the answer matrix all kind of shoved into one matrix there. Okay, we're not going to be using inverses to solve this, so you know. Okay, so it is not a problem that this matrix is not square. Okay, but really what's going to happen here is we're going to reduce this matrix, kind of like reducing a fraction. We're going to reduce it down to a point where we're going to build zeros inside of the function in a certain way, so that once we're done building our zeros, what's left over, we'll be able to take a look at it and just read the solutions for x, y, and z right in the matrix. Okay? Oh. Some teachers like to do this. Is that helpful if you put the little slashy thing inside the z's? Okay, well, anyway. Sorry, well, anyway. Yeah, there are going to be z's over there. So, think about in a system. In a system of equations, what are some rules, what are some things that you're allowed to do with those equations to help you solve it? Okay. So, one thing that you can do, and stop me if you disagree. Looking at you, Matthew. So, one thing that you're allowed to do is the order of these equations does not matter. If I were to take this third equation down here and just write that as the first one on top, doesn't change the system, right? Still the same three equations, right? So if I'm allowed to do that to this, shouldn't I be allowed to do it over here too? Yes. So the order the equations are written, so over here, I have rows without any trouble. Okay? So number one. So since we can swap equations, then over here I'm allowed to swap rows.
You have to swap the whole row.
Yes.
At all.
Yes. Yep. It all comes along with it. Okay. Something else. Again, stop me if you don't agree. But the order that these variables go in doesn't matter. I could have written it with the y's first, then the x's, then the z's, and then the answer. They do. Correct. So you can swap an entire column. But not the augmented part. Right. These columns, yeah, that would be a little confusing. Well, I guess, no, if you did that, you'd have to change the sign, but it would get really confusing. You could, I guess, but it's not really the accepted way of writing these things. But mathematically, you could get around and make it work, yeah. What I'm trying to make is, within this matrix, the non-augmented part, you can swap columns without any trouble, okay? The only thing you really have to worry about with that then is, if you're going back and solving this thing when you're done, you have to keep straight what's x, what's y, what's z, though, right? So it's kind of a bad idea. It's mathematically okay to do, but it doesn't really solve any problems for you usually. So, because it is something you could do, but in practice, it's not something you're going to want to probably do.
Why are we bringing this up then?
Oh, here's the thing. You could do it this way. If the original equations were written in such a way where it didn't go x, y, z, it's okay to rearrange them so that they do go x, y, z. That would be a time you'd want to do it. So, but next to it.
Why wouldn't you just switch the equation before converting them?
That's probably generally what you'd want to do to make it easier on yourself. But if it was already in a matrix, you could then swap the columns to make it the way you wanted it.
And how would you know what x and what's y?
Okay, so let's say this. Let's say we're not talking x, y, and z. Let's say we're doing some kind of real-world application, whatever, and the three variables were three completely different letters, like an L and an H and a T or something. And it doesn't really matter what order they go in because you're just looking for three things and you don't care what's what and where it is. But it makes solving the equations a little easier if like two of them got swapped around. Then maybe you'd want to do it. We're going to stick with x, y, and z because it's what you're familiar with, it's what you know. So we don't really have a reason to do that where it takes x, y, and z and puts them in a different order. But if you got something else, maybe you do. I don't know. I mean, it doesn't, in general, it doesn't always give you a leg up, but maybe it looks a way that makes it easier for you to see what's going on. I don't know. Anyway, let's continue. You are allowed to take any equation and multiply by any number you want. As long as you multiply both sides of it, right? I can take that entire first equation and multiply it by 2 if I wanted to. Now, in this particular system, would that help me? Maybe not. But you are allowed to multiply an entire equation by a number. So let's write that down.
Why are we doing these if we're probably not doing these?
No, you are. This one for sure.
I still feel like the second one, why did you bring it up?
Just erase it off your paper if you're that upset about it. Whatever. Whoops, an entire equation.
You're basically saying what you can do the equation, you can also do the matrix.
Yes. Take equation lingo into matrix lingo.
But it's the same number.
No, it's not. The lingo changes. It's the same mathematical operation, though. So multiply an entire equation by a constant means you can multiply a row by a constant.
Wouldn't that be like a scalar?
Nope. It's only a scalar if you didn't have the augmented part of the matrix. So if we were thinking like vectors or that sort of thing, and you multiplied every part of a vector by a scalar, then it scales it up. But as soon as it's equal to something, then all you're doing is you're keeping that equation equivalent. You're keeping it the same as what it was by balancing both sides by the same amount. And we'll talk about when you want to do that, because that's something we'll do a ton. Number 4, we are allowed to add equations together and subtract them together, right? Solving systems using the elimination method, we've done that. Let's see, so we can add / subtract.
So you can basically just take all that and just put it all into one equation.
Sure. If we were to add that all up right now, would it really do any good?
Yeah, but you get rid of y.
Oh, yeah, okay. So, okay, usually adding all 3 equations together isn't going to do much. Now, why? You'd be stuck with x and z still, right? Can you solve one equation with 2 variables in it? Mm-mm. So that wouldn't help you right now. Now, if you were to choose 2 particular equations in there and add them together to get rid of one variable, that would be a good idea. That would get you somewhere. And then you could use that new one with one of the ones you still have left and see what you can do. But
Like, it'll be easy to solve. Add the top 2 and then add the result to the bottom one. And then you have at least.
No.
You could add the bottom.
You'd still-
and
you'd-
eliminate 2 variables.
No, if you added the top 2,
yeah,
Z would cancel.
right.
If you add that resulting equation to the bottom one, Y cancels.
And you'd reintroduce z.
You'd reintroduce a negative z.
Yep. You'd be adding the negative z to what you had, and then you'd have z in there again. So here's what's going to happen. You're going to multiply equations by scalars and then add or subtract them to eliminate certain things. Add or subtract them to other ones where you don't reintroduce a variable you already got rid of. And keep working it down until you have just what you want. No, it's not. It's pretty awesome, actually. Means you can add and subtract rows. Right? So that's another something. And with this too, that includes the augmented part too, right? The answer, the equal part of that. Those have to get added up together as well, and you have to kind of keep track of what's going on over there as you're working in your matrix. So ignoring the second one, because apparently you guys don't like it, 1, 3, and 4, do you see how it all has to do with rows? Okay? Row operations. There you go. Those are your row operations. Those are things you're allowed to do to the rows to help reduce the matrix so that you can get your answer. Okay? Here's how we do it. We were going to try our matrix down to what's called echelon form, which is make zeros in the matrix. That's what echelon form is.
What language did that come from?
I don't know where this came from, the name of it.
I was thinking Klingon, but yeah, a little bit.
So if I a 2 by 2 matrix, echelon form would look like that. That's a 0. If it was a 3 by 3, echelon form would be A, B, C, 0, E, F, 0, 0, I. So you're making a little triangle of zeros in the bottom left corner. If it was 4 by 4, A, B, C, D, 0, F, G, H, I, J. They're zeros. J, H, I, J, K, L, M, N, O, P.
No, and that's a 0 and not an O.
Correct. Just totally happenstance. Okay, so work making these little like zeros in the bottom left corner of these things. Because think about what you would have left. You still have the augmented part of these, right? So then, hold on just a second. Let's say this is like, this would be like, let's say it's a 2, okay? So this would be like 2z equals some number. Which is what the equation would be. You can solve it then, right? Well then, once I know z, Go up to this one. Something times y plus something equals this. Y. Y and z. Here I can work backwards. I can. Okay. So it sets up a matrix where you can just substitute your way up the equations and keep getting all of the variables that you need. Okay?
How do we do that?
Yeah, row operations is how we do that. Okay? So that's what I'm going to do. So I'm going to show you how to get through here. So we're going to use row operations, bless you, to get echelon form. All right, so let's do an example, and I want to make sure I get one here that actually works. This one works. Okay, so x minus y plus 2z equals -3. 2x plus y minus z equals 0, and -x plus 2y minus 3z equals 7. All right, we're going to go with that one. So what you have to do is put that thing in an augmented matrix. Strip off all the variables and rewrite it as a matrix. So we're looking at 1, -1, 2, 2, 1, -1, -1, 2, -3, augmented with -3, 0, 7. Okay.
It comes from the word echelon, which means rung of a ladder.
So those three numbers in the corner there, that's my zeros to be, right? Reintroduce something that I've already gotten rid of. Once I've got a 0 somewhere in a position where I want there to be a 0, I lose it. I don't want to go back and do my next step and then all of a sudden that 0 I have to take off of there again. Okay? So there's a bit of an order that you have in how to introduce your zeros. Okay? So we want to kind of build them up starting with this column. So this one in the very corner is our first one. Then this one, then that one. Okay? So let's think for a second how we could get a 0 here doing some row operations. I'm allowed to add rows together. I'm allowed to multiply rows by certain things. What do I do to get the 0 there? What kind of operation? Yes? We could. Yep. So here's how we represent that. So we're going to do row 1 plus row 3 equals row 3, which means I'm going to replace row 3 with the addition of row 1 and row 3. Okay? Let's see what we have. So,
Just leave row 1 there then?
yeah. 1 as it is. In fact, row 2, nothing's going to change.
How does that work? Why would you just be able to leave row 1 there if you're adding it?
Because it's still a true statement.
Exactly. It's still an equation in the system.
Oh, because
This little equal sign is key. I'm just using row 1 as a means to get a new row 3. Okay? Row 1 plus row 3 is going to give me my new row 3. So the old row 3 is going to go away. Okay? So 1 gives me 0. 9 plus 2 gives me 1. X And 2 plus negative 3 gives me negative 1. And then I have to make sure the augmented part, negative 3 plus 7 is 4. So now I've got a 0 in that position.
Can you only have zeros in those three spots?
You could have more.
Why don't you just multiply everything by 0?
Because then everything is 0 and you have no solution.
It's still got zeros where you need zeros.
Yeah, but not in the way we want them there, though. So, well, yeah, you go ahead and do it your way and see what happens, because you're not going to have a lot of luck. Anyway, so the next 0 we have to go after would be changing this 2 into a 0 without just multiplying everything by 0. So, if you notice, you still have the top equation to work with. This bottom one, though, is not going to assist us in making this a 0. You guys see that? I can't add something with 0 to 2 and get it to turn into 0. You know what I mean? That's not going to work. So, how do I calculate row 1 so that it is now useful in helping me to get rid of this 2 and make it a 0? You think you were first? You got it. You want to do it as 2 separate steps, more power to you. Eventually, we're going to get to a point where you can start to do those in combination. Kind of like she just said, take the top row, multiply it by negative 2, and then add it to the second one. Okay? Yeah, and you can leave the top row alone. Yeah. So, let me try. You guys can follow me here with that then. So what I'll do is, F will be 2, row 1, plus row 2 equals row 2. You with me there? Every time you do a row operation? I would, just so you don't lose track of what you were doing. If you just, well, that's just the thing, though. I mean, like, if you were to go through and just start reducing, and then you're like, oh, crap, I made a mistake, and you have to go back and figure out where it was. If you don't know what the row operation was that you were using in a given step, I mean, each matrix is just a whole bunch of, it'll just appear to be a whole bunch of random numbers. So how the heck are you supposed to diagnose what happened when you go back? So I encourage students to always write down the row operations that they're doing so then they can figure out, if I did make a mistake, let's double check the row operations and make sure I actually did the numbers the way that the operation said I was supposed to, and it helps a lot. So yeah, I'm going to make you do it. So we're replacing row 2, which means row 1 and row 3 are not going to change, right? Those are going to stay the same. So that's going to be the same, and then this one that we had already gotten, stay the same. And you can do this math in your head. So negative 2 row 1 plus row 2 is what we're going to be putting in each of these places here. So we got to go back to this other one over here. So negative 2 times 1 plus 2. 0. So next question, negative 2 times negative 1 plus 1. Negative 2 times 2, negative 4 plus negative 1, negative 5. And then the next one, negative 3 times negative 2, plus 0. Okay, so we're getting there. Yeah?
I don't understand why row 1 doesn't change.
Because we're not replacing row 1. We're simply using it as a tool to get row 2 the way we want it to be.
Okay. So they're not next to each other, besides the fact that you're using the same number.
Yeah, I'm using the numbers in row 1 to help me get row 2, but I'm not actually in my matrix changing row 1 at all. And in fact, if you do this correctly, by the time you're done, row 1 at the very end should look exactly like row 1 did at the beginning. Should have no change at all. Question?
If we have like a 4x4,
Mm-hmm.
and you have the triangle right up top,
Yeah.
you said to start in the corner,
Mm-hmm.
and go around.
No, you want to go up. So we did this one first, then this one, then this one. So up here, your order that you would want to get your zeros, you'd start here, work your way up this, and then get this one, and then this one. So kind of each like that. No, no. Because now that these are both zeros, again, don't do anything to row 1. Only use row 2 and row 3. Any linear row operation that I do on these two have to stay 0. If I multiply this first equation, or the second equation, or the third equation, what is the 0 going to be when we're done? 0. And if I add or subtract those two zeros in any way, what are they going to be? Zeros. So by getting these two first, I've ensured that I'm never going to change them, no matter what I do. With those 2 and 3, though. I can't go back to row 1 because that might screw the deal, right? Because there's still a 1 hanging out over there in the first column, and that could change something. So if I just stick with rows 2 and 3, I last 0. But I got to think about, again, what kind of operation can I use that's going to make that happen then? So any ideas of where we could go next then? Yeah, go ahead. You got it. So negative 3, row 3, plus row 2 equals row 3. Okay. And then, so row 2 is not change, right? 0, 3, negative 5, 6. All right, so this last row. So just to make sure I'm good, negative 3 times 0 plus 0. So again, we're keeping that 0. The next would be negative 3 times 1, negative 3, plus 3, 0, which is by design, right? And then the other ones I got to just make sure I find. Negative 3 times 1, plus negative 2. And then, let's see, negative 12 plus 6, negative 6, yep. Once you get the hang of it, it goes pretty fast. The only real, hang up with this, once you're good at it, is you have to keep drawing out the whole matrix every time. So that gets a little bit tedious doing that. But the work you're doing in doing that versus if you were to try and take this 3x3 system and do a whole bunch of substitutions and eliminations or whatever else you were going to do, it actually is a lot less work than trying to mess with all of that. This stage, we're ready to go to solve it, right? Because we've got that little triangle of zeros like we wanted. I could simplify this matrix just a little bit more to make it easier to read off my solutions. Okay? If each one of these numbers down the diagonal is a 1, then I don't have a coefficient in front of the variable I'm trying to solve for each time, which makes things a little nicer. Okay? So I encourage you to do that. If you don't want to, it's fine. You could just start negative 2z equals negative 6, get your z, and just keep going back and doing that. One step further. See if you can follow what I did here. And this really isn't a difficult step to do. So my doesn't need to change because the first coefficient's already a 1. The second row, I know it's going to introduce some fractions, but really it's not going to hurt anything. Okay, anybody catch what I did there? What row operations did I do to get this last matrix? Yep, because remember I said you can multiply a row by whatever you want, which implies then that you could divide it by whatever you want too, because it's really just multiplication either way. So, operations, I guess it would be row, what would it be? I divided by 3, so 1/3 row 2 equals row 2, and then I did negative 1/2 row 3 equals row 3. So I replaced those two rows by doing a little bit of division. or multiplying by a fraction. And I got that. So, just looking at that matrix then, what's z? 3, because this equation down here has been reduced all the way down to 1z equals 3, right? So, boom, got it. Z is 3. Now, the equation right here is y plus negative 5/3 z equals 2. So y minus 5, but I already know z, right, is 3 equals 2. Seven. Add 5. All right, so yeah, y is 7 then. And this time, x minus y, but again, I already know y. It's 7 plus 2z, but I already know z, it's 3, equals negative 3. So then I can work backwards with that and figure out x. So x, this would be 6 plus 7, that's minus, negative 7 plus 6 is negative 1. So x would have to be negative 2. So I was able to solve that system at the end pretty effectively once I had that reduced matrix to work with. Okay? 0's in the corner triangle, 1's on the diagonal. It's usually pretty easy from there. Just keep back substituting into those equations that you have left. And when you have x, y, and z, remember before when we solved systems, I made you write it as an ordered pair? This is an ordered triple. So we have to write it x, y, z. An ordered triple. So I don't have any room at the bottom of my page, but right here, your answer would look like this. Negative 2, 7, 3. And think about this. If this was a system, if we're talking 3 variables, 3 dimensions, so if you were going to plot like a point like this, it would be in 3-dimensional space. It would have an x-coordinate, it would have a y-coordinate, and it would have a z-coordinate. It depends on your reference frame. But I'm thinking x is this way, y is going this way, and then z is up and down. Well,
It doesn't matter.
you're looking down on it rather than from the side, but same diff.
The side rather than down.
Depends on what you're talking about. Never mind. You're talking about z. You're looking at from the side of z or down on z. Okay. Yeah. Then you're right. Yeah. Yes, Josh. Question.
In theory, couldn't you technically use the other corner?
Do what?
Are you using the bottom left corner for all the zeros?
Yeah.
Could you use like the top right?
You could also use the top. Mm-hmm. Yep. It is just kind of a little more accepted to do it down here, but I guess mathematically, technically speaking, x, y, and z, they're all kind of the same deal, right? They work the same way, so you could go up or right on it. Yep. And it would work. Want to try one more on your own?
Yeah, let's do it.
Last thing we do today, if you do one on your own. How about that? All right. It's going to work out for you here. Answers that are not fractions or have radicals in them. Who did that?
You're still not doing something wrong.
Have radicals in them. Just avoiding.
Oh, so if you get radicals, you are doing something.
Yeah. Yeah. All right. Yeah, this one should work. So let's try. So, remember you're being recorded. Okay, so that's going to be your system. Try it all on your own. So make the augmented matrix, do your row operations, getting the zeros in the order that we talked about or where you want them, and see if you can solve it that way. And I'll stop recording now. Okay, so I'm going to put a system down here, and I want you guys to put this into a matrix for me, or just see if you can. 2y equals 4. 3x plus 4y equals... and 2x plus 3y equals 4. So take a second, see if you can put that in a matrix. An augmented matrix. Nope. Not yet. Just put that in a matrix. Now, usually, when we have 3 equations, we also have 3. Yeah, we don't have that, right? So a couple different ways you could approach this. You could just not even deal with the z's and just make each line 2 numbers and then the augmented part. Or you could just put a bunch of zeros in there for the z's and have it a 3 by 3 and do it that way still. Okay. Either way, we will be getting the same thing here. So I'm going to do zeros because I like to keep things looking square, but it will work without as well. There are no z's, so I'm putting zeros in for z's. I like things that look square because then it's easier for me to visualize what I got to do. I meant the coefficient matrix was square. Okay? You know what I meant. Anyway, our goal is to get those all to be zeros. So let's think about some row operations we can do to take care of that here. So, any ideas? Where do we start? Yes.
Since we can move the columns around,
Mm-hmm.
we could just move the right column to all the way to the left and get the 2 zeros there.
Hey, there you go. That's a good first step. So there's a...
Remember that it's x. Yes.
What if we didn't put in the zeros? You still want those 3 numbers?
if you didn't put any zeros in, then you can't swap the column like we're doing right now. And you're going to have to work on some other row operations to get zeros in your little triangle there. And then we got 2, 4, 3. Wow, okay. I did a little shift, but either way. So Z, X, Y. Okay, so that's where we're sitting now with our variables. Okay, so yeah, I made a good point. We've got the first 2 zeros taken care of already then at that point. So now we only need to get a 0 down there, right?
Do we not like section anymore?
Oops. Hold on a second.
Thought I'd ask.
Oh, I don't want to neglect the augmented part here. Ms. Barks, tell me again what we're going to do. Yeah, -2 would do it. If you're going to add.
Why can we not call you back to number 2? But you can call her Miss Marks.
Maybe I found that disrespectful. You don't know
Anyway, so 0, 0, 0, negative 2. Now this all stays 0, right? That makes sense because no matter what row operation you do to that column, it's going to always be zeros. So the next row, this should stay the same. This should stay the same, but we're replacing row 3 with negative 2 times row 1 plus row 3. So that's going to produce a 0 there. And then this is still a 2. This is still a 4. And then negative 2 times 2 plus 3 gives you negative 1. Yep. And then over here, so negative 2 times, what do we have? 4, so that's negative 8 plus 4, negative 4. So this should be 4, negative 4. Okay, seems to be on the level still, all right? We should be able to do our little back substitution maneuver here and get our x, y, and z. Keep in mind, though, this is z, this is x, this is y. So really, we're only going to be solving for x and y, right? They were the only two variables that started off in this set of equations. So, all right, so let's take a look at the bottom row here. Negative 1, negative 4. What that implies is that negative z equals negative 4. So, I'm sorry. I caught it right when you said it. So, if negative y equals negative 4, what is y? 4. Okay. 3x plus 4 times 4 needs to equal 5. So 3x equals 5 minus 16 would be negative 11 thirds. Okay. And looking at this right here, we might be like, sweet, we got them both, right? We got x and y, everything's fine. Still that first equation that must be satisfied as well. X plus 2y equals 4. That's part of the system, and we can't ignore it. It has to work too. So x plus 2y needs to equal 4. So, got to take these two numbers, put them in, see if it works. Negative 11 thirds plus 2 times 4 equals 4. No. Doesn't work. You plug those in, it doesn't happen. It's kind of like when you guys remember like when we had to like check for extraneous solutions when we were doing all the like rational expression stuff. It's kind of like that. There's all these equations that have to work with these numbers that we've come up with, and if it doesn't work for all of them, then no solution to the system. Okay? Okay, so in that case, no solution. And you won't know that unless you go through the process of trying to solve it and figure out, oh, that doesn't happen. Now, one thing, some people might say, well, if you look at the original system here, there weren't enough variables for the number of equations that you had. So you could just say right there, no solution, right? Not necessarily. Yeah. It could be that each one of these particular equations, if I have the same x and y that work, will work for those. Okay? It could just be a different looking equation, but if you plug the numbers in, it works. It works. It works. You don't know for sure. So you got to go through the process to figure it out to see if it actually is going to work or not. So, yeah. So that's your no solution case. Okay? And all you got to write for your answer is no solution when you get to that. Or if you like the little symbol, that's the symbol for no solution. It's a little circle with a slash through it. Kinda, yeah. Other situation, what if you end up with something that has an infinite number of solutions instead? And we've got a different way of writing those answers now, so we're going to look at that. A way of using some formulas in the answer to describe what those infinite solutions really are. Okay, so let's take a look at that. See if I can find the system that we got here. Yeah, okay, so x plus 2y minus 3z equals negative 1. 2x plus 3y minus 4z equals... Oh, is that the one I want? Stop for a second. Sorry, I was looking at the wrong one. You'll thank me in the long run, but a much more difficult to deal with one. Y plus z equals 3. 2x plus y plus 4z equals 8. And then x plus 2y minus z equals 1. Take a look at that system. So, seems normal enough looking at it. So, let's encode this thing into a matrix. So, we got 1, 1, 1, 3, 2, 1, 4, 8, and 1, 2, negative 1, 1. Okay, so, get me started. Give me some row operations.
Row 1 minus row 3 equals row 3.
Sounds good. So row 1 stays the same. Row 2 stays the same. Row 3 we're going to subtract. Row 1 minus row 3, so that's 0. 1 minus 2, that's negative 1. 1 minus negative 1, that would be 2. And then 3 minus 1, 2. Okay. So we got our first little 0 in the corner there. Where do I want my next 0 to be? Above it. Okay, so somebody give me a row operation to make that happen then. So 2 row 1 minus row 2 equals row 2. So first row, still the same. Second row, 2 minus 2, 0. 2 minus 1, 1. 2 minus 4, negative 2. And 6 minus 8, negative 2. And then we still got the same bottom row, 0, negative 1, 2, 2. Anybody notice anything? It completely cancels everything. And remember, we want to get a 0 here next, right? To be able to do that, the row operation would be row 2 plus row 3, right? Exactly. Yeah, that's going to create a problem because this 1's going to come down here to this 0, right? You have to use row 2 and 3 to do what we want to do. You cannot use row 1. So it's going to cancel everything. So it's going to leave us in a little bit of a lurch here, but I'll show you how we can get through that. So row 2 plus row 3 equals row 3. We got to do it. So 1, 1, 1, 3, 0, 1, negative 2, negative 2, and then we get 0, 0, 0, 0. Okay, so what's happened now is that bottom equation, meaningless. There's nothing there. There's nothing you can do with it. So we really only have 2 equations now. By trying to do these row operations, we've taken our 3 equations we started with, and we've really broken it down into just 2 now. And so I'm going to rewrite what those 2 equations say. We have x plus y plus z equals 3, and then we have y minus 2z equals negative 2. I have 2 equations. I have 3 unknowns. Can I solve that system then? Not for any one specific point. What we have here is infinite solutions. It's an infinite number of combinations that will work for this. Okay? So we can't possibly list all the answers to this, all the ordered triples that will do it. So what we do is we write an ordered triple, but we write it as kind of a bit of a formula. Okay? So if we can write one variable in terms of some other ones, then we can do that instead of just writing numbers in there. Okay? So consider this second equation for a second. Okay? Y, if I equation for y is equal to 2z minus 2. So I can write y as a function of z. Okay? And then x is in terms of both y and z. So since I have this solved for y, I substitute it into this top equation then where I see a y. And so I'm going to rewrite that one for just a second here then. So x plus 2z minus 2 plus z equals 3. And then I got some like terms and things that I can kind of shuffle around here. So x plus 3z, if I add the 2 to the other side, that's a 5. So x equals 5 minus 3z. So I'm able to, through a little bit of substitution work here at the end, write x and y as functions of z. So while my solution can't be number, 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 I can write each coordinate as a little equation involving z. So as long as I pick a z, I then know what my x and my y have to be to go with it. Does that make sense? So I could say there's infinite solutions, but if you happen to pick a 1 for z, x and y have to be these two things. Or if you happen to pick a 2 for z, x and y have to be these two. See how that works? So it's easier to use. It's like having an ordered triple. That's a formula that, yeah, there's an infinite number of solutions, but whatever you pick for z, you can quickly figure out what the ordered triple needs to be for that specific number that you have. So z ordered triple is going to be minus 3z, 2z minus 2, and then just z. So the answer ends up being like a formula, like I said. We're going to attack infinite solutions, okay? So you take what you have, write the two equations or however many they are at the end that you have, and then using some substitutions, you're going to try to write variables in terms of one of the ones you don't know, okay? And in this case, we're able to do it where everything we could write in terms of z. But it's not always the same little cookie cutter type situation. It could be different. So maybe you want to write things in terms of x or whatever. Just whatever makes the most sense. Okay. In this case, z seemed to work out the best. So we've got everything in terms of z. And then, yeah, that third one, because I don't need a formula for z because it is just z, I just leave it z, and that's it. Okay. So infinite solutions. You don't run into that a whole ton. I've got at least one, maybe two that are in your assignment for you to try. They really are kind of the strangest, though, of all of them that you have to deal with. Other than those, it's pretty straightforward, same type of a process that you do with everything else. Okay. So, any questions for me before I set you loose on doing some of this on your own? We're good? Okay. Then that's what I will do.